Hello and welcome back, everybody. Today we are looking at the second part or second half of the integral test in section 11.3. So the last thing we did was the integral test to be able to determine if a series is going to converge or diverge. Now remember, in order to take the integral of the function that you're using for convergence or divergence, you have to make sure that there are three properties that you have to fulfill. Number one, that it's always positive. Number two, it's always continuous. And also number three, that it's monotonically decreasing, meaning that it's consistently decreasing everywhere about within that domain that you need to use. Okay, so let's go ahead and continue on with the integral test to introduce something called the error bound. So in this case, here is a problem that I'm going to present then. I want to estimate what is the I want to estimate what is the summation of the series over here, 1 over n cubed from 1 to infinity using the first 10 terms. So what that means is, as you can see, this is something that is going to be decreasing. It's always continuous and it's always positive. So therefore we can use the integral test. Now the problem is if I take something like this and put it into the calculator, which you actually can, because if you go to the math setting and then you scroll down and you see the summation sign, and then you can actually enter the summation that you actually have. The summation starting from n is equal to 1 all the way to however many terms you want of the equation that you have inside. So for example, I can actually put in like say 20 terms or 30 terms or so forth. But the problem is, in our scenario, we want to sum the infinite number of terms. And the last time I checked, when I tried to put in something like, say, 9,999 terms, the calculator definitely did not like it. And as a result, it just kind of kept going and going and going. And even after, like, say, 2 minutes, I couldn't get an answer. But it's not to say we need to actually sum up all of those terms because, well, that actually takes too long. If you notice, the terms are going to get so insignificantly small that eventually it doesn't matter because you're adding a bunch of zero. And hence, that's why we can use the integral test in this case, because the limit as the function approaches towards infinity, as the number of term goes to infinity, it goes to zero then as a result. So what I'm saying in this problem is, hey, I want you to estimate what I want, but using only the first 10 terms. So that is something that you can definitely put into your calculator and solve for. And just to save a little bit of time, we can go ahead and show that right now. So if we go over here, I'm going to go to the calculator. And let's see, we're going to go to the zero summation right here. So let's see. Oh, I got to clear that up a little bit. So go to math, and then we're going to go to summation. So we're going to go ahead and use x is going to go from 1 all the way to 10. And then it's going to be 1 divided by x raised to the third power. So there you can see that the summation is going to be approximately 1.198, I guess, in this case. So let me go ahead and put that in right here. So in this case, this is using a calculator. That is going to be equal to 1.198. And for the most part, that is somewhat close to our answer without having to, blow up the calculator, because I don't want to I don't want to ask the calculator to do, like I say, 1,000 terms unless you have one of those super calculators. So there it goes. That's going to be the estimate then using the first 10 terms, something that's, within human grasp. Now, the question then afterward is, what is the error that is going to be if you're using the first 10 terms? Meaning, like, how accurate is this going to be? Well, here in this illustration on the right-hand side, you can see that I kind of like gave a generic sketch of the graph then. So you have a of n is equal to 1 over n cubed, and you're summing the first 10 terms. Now, since I want the whole thing, then that means I want the sum of all of these partitions. So whatever is left, or whatever that I did not calculate, that right there would then be my error then. So then that means that in terms of where we're looking at for the error, it's going to be everything that's going to be after 10. So all of these guys, okay? So the question is, okay, well, how do you actually estimate that then? So then one thing you can think of is that the error is going to be everything after the 10th term. So the error is equal to everything, okay, after the 10th term, okay? All right. Now, the question is, well, then how do you figure out what that is? Well, one way you can do it is, well, as we said, just using somewhat like the integral test. So what I'm thinking of is probably something like the following. We're going to go ahead and look at the integral of from n, in this case, which is equal to 10, all the way to infinity of 1 over n cubed dn. So right there, that'll give me like an estimate as to what the error is. Now, the reason why I can do that is when you're looking at these partitions and you're using the integral, you're looking, that's, thinking about how we did it in the past, right? Partitions under the curve is what makes up these integrals. And since there are infinitely many number of them, we can use the integral to estimate it. But it is not going to be an exact value. This is just going to be somewhat of an estimate. We can only get like an idea as to like what it's going to be about approximately. So here, if I solve for that, we can then find out what's the error then approximately. So this is where your indefinite integral is going to come in then. So we will write it as limit as t approaches towards infinity of the integral from 10 to t of 1 over n cubed dn. Take the antiderivative. So limit as t approaches towards infinity. The antiderivative of 1 over n cubed, that's going to be negative 1 over 2 n squared. And the boundary, again, from 10 all the way to t. Okay. And then as a result, we're going to go ahead and plug things in. So limit as t approaches towards infinity. So negative 1 over 2 to the n, 2 times n squared. And then when I plug in the boundaries, my upper bound, let me go ahead and put that in there right now. Okay. So my upper bound is going to be t, and then minus my lower bound, which becomes a positive because of the negative. 1 over 2 times, what is it in this case? 10, and actually, wait, hold on. I think I messed up over here. It should be t squared. My fault about that. Okay, sorry about that. So here's t squared, and then this is going to be 10 squared in this case on the bottom. And as the first term is driven to infinity, then that means that goes to 0. So what's that left with is the 1 over 200 right here. And that right there is going to be the estimate of my error then. Okay, so that is approximately 0.005 then. Now, this guy right here, this error that I found, that's actually the upper bound of the error, meaning that your error is going to be actually less than that. So, and the reason why is, well, I'll show you underneath in just a little bit. So the error is going to be less than 0.005. The reason why that's the upper bound is, well, again, thinking about like, how you solve for the area under the curve, how we introduced it. You have two ways of solving for the area under the curve. If you remember from the very beginning, it was either use the left-hand rule or the right-hand rule. What's going to happen is that when you use the left-hand rule versus the right-hand rule, one's going to be an overestimate, the other one's going to be an underestimate. So here in this illustration underneath, you can see that we have two different scenarios here. You can see that on the left, you have an integral, which is going to be an overestimate then. Whereas on the right-hand side, you have an integral that could be an underestimate. So it could be either one or the other. But the biggest difference between the two in terms of like, how they're related to each other is that, well, if you think about what we did back with the left-hand rule and the right-hand rule, the right-hand rule or the left-hand rule, whichever one it is, that's the overestimate and the underestimate. The underestimate was always just one partition less than the overestimate. Let me repeat it one more time. The underestimate is always just one partition less than the overestimate. So in this case, what that means is that there is actually a nice bound that we can actually figure out what the error is going to be between. So here, let me just kind of set it up then. Here, in short, what I was trying to say is the following. Your error that you're trying to find is bounded above by the integral from 10 all the way to infinity of a of n dn. Whereas for the other one is going to be, let me go ahead and write this a little bit better because I don't want to write the summation sequence notation for this, of a of n dn. Whereas for your lower bound, right, your lower bound is going to be from 11 to infinity of a of n dn. Because as I said earlier, your overestimate is going to be always one more term than the underestimate. So that's why in this case you start at 10 because, well, we use 10 terms, and there are like any terms after 10, that's going to be your error in this case. And one less term than that, that's going to be 11 because you don't count the 10th term in this case then. Okay. So here's the next question then. What is the upper and lower bound of the series for using 10 terms? Well, here we have that set up. Okay, here we can see what the error is in this case. I want to know, basically in short, that if I were to use 10 terms, right, what is my upper limit for using 10 terms, and what is my lower limit for using 10 terms? Like, how is it bounded by? Okay, so here we can go ahead and actually solve for that. And I feel like what we did previously is going to help out over here, right? Because this guy right here, let me just go ahead and box it, is going to allow us to determine what that is, because we're going to have to use it again. Here, let me just go ahead and write it out. If I were to, expand this out, it would say limit, right, as t approaches towards infinity of 11 all the way to t of 1 over n cube dn, and then it's less than the error. So the error over here is less than the limit as t approaches towards infinity from 10 all the way to t of 1 over n cubed dn. Okay. All right. Those we can solve for. And in fact, I want to recycle what we did previously. If you remember, just going by what we did, and going to what I boxed over here, we can actually quickly solve the answer, because if you notice that the procedure is pretty much going to be the same thing as these three parts over here. So what that's going to end up with is the following over here. This guy, if you remember, we just solved for earlier, that is going to be between 1 over 2 times 10 squared. Okay, so that's going to be my upper bound. And then for this one over here, my lower bound, that's going to be 1 over 2 times 11 squared. So there's my lower bound, there's my upper bound, and that's going to tell me what the error is in between. Now, I don't want to actually solve for that. According to the problem, I want to know what is the upper bound and the lower bound of the series for using 10 terms. So what that means is if I solve for the series, I want to know how big is it going to be at most and how small it is going to be at most. So what I'm going to do is take this inequality and I'm going to add on a certain part to it. And that certain part is, well, the series all the way to the 10th term. So s of 10 is going to be added to all three parts. So s of 10 plus 1 over 2 times 10 to the 11th. And then is less than, for the next part, is going to be s of 10 plus the error. Okay. And then after that is going to be less than, once again, s of 10, and then plus 1 over 2 times 10 to the second power. Okay. Those values we actually know because we saw for s of 10 earlier. That was approximately equal to 1.198. Okay, so here on the lower bound, it's going to be 1.198 plus this guy over here. Okay, and then my upper bound is going to be 1.198 and then plus the upper bound in this case over here. Okay, and in between, now that right there, s of 10 plus the error, that's the entire series. Okay, so that's the series itself if I were to, sum up every single term. So right there, that's going to be our answer then. Okay, so just kind of solving this for you guys. Let's see. This is going to be 1.202 solved for ahead of time. And then the other one is going to be 1.203 in this case. So your series, if you were to use 10 terms to estimate what it's going to be equal to, is going to be somewhere bounded between 1.202 and also 1.203, which is actually pretty good then for the most part. Sometimes people say that the error would then be approximately the average of the two then. So the error, okay, which is going to be the average error that we're referring to, is going to be 1.202 plus 1.203 divided by 2. And it comes out to be 1.2021, actually, if we were to use more decimal places. Okay. All right, so that is going to be how we solve for the error. And now for the last part, well, what if I want to find out how many terms do I need so that my error would be within a certain boundaries, because I think that's probably more important. So then that way we don't we don't kind of like overdo things. Okay, so I want to know how many terms do I need so that my error would be at most 0.0005. Well, going by what we said earlier, right, then that means that we're going to have to do the following. I want to know how many partitions that I solve for, right? So that means that S of n, right, the summation of a certain number of terms, the sequence, is going to be less than or equal to the, not the, sorry, let me go ahead and kind of rewrite this over here, okay? S of, let me think. Sorry, yes, you're right. So S of n is going to be less than the integral from n all the way to infinity of 1 over n cubed dn. And that right there is supposed to be then less than 0.0005. Okay, so note how we took the error part right here. Okay, so this is going to be my series. I want the error right here, okay, which we said is supposed to be the integral from earlier. And we want to say that it's going to be less than 0.005. So note in this case, what we can do is then solve for what the value of n is going to be according to this integral. Okay, so once again, we're going to go ahead and take the antiderivative using the, what was that called? Improper integral. But if you remember, we were supposed to be able to kind of just like, we can just go ahead and use this part right here. This guy right here, sorry about that, to figure it out. So the result is that this is going to be 1 over 2 n squared, and then it's going to be less than 0.0005. Okay, so here we can go ahead and cross multiply everything, and when we just clean this up, then you're going to get n squared is going to be less than 1 over 0.001, which is equivalent to 1,000. So if now I take the square root of both sides, then that means n has to be greater than 31.623. So that tells you that when n is equal to 32, or anything that's greater than 32 terms, greater than or equal to 32 terms, then your error would then be less than this result over here. Okay. All right, thank you so much for watching. I will see you guys next time then. Goodbye.